All right, welcome back, everybody, and thank you so much for supporting the DEFCON community and especially the Red Team Village. And without any further ado, I pass it back to Gabriel. Take it away.
How you doing, everyone? This is it's a little different, but yeah, this is I'm introducing a new tool called Drop Engine. It's a malleable payload creation framework. A bit about me. Won't go on about this for too long, but my name is Gabe Ryan. I'm a Red Team operator at SpectreOps. I used to work in a place called Gotham Digital Science doing security consulting. Got my Twitter handle and my LinkedIn username is actually pretty interesting. It's MS08016. But so without further ado, let's just dive right into this. Let's talk about initial access payloads. So, what are initial access payloads as opposed to like normal payloads? Initial access payloads are typically used to gain access to a system environment. So at the very, start of your engagement, it's what you're using to essentially gain your initial foothold. They're pretty simple in design. I mean, it really has like one job, which is to execute an implant or second stage payload, and then from there you pretty much do everything. All your secondary endpoint operations happen from that point onwards. Colloquially, they're also known as droppers or shellcode runners because they run shellcode. But yeah, while initial access payloads do have a pretty simple role, there are some obstacles that you have to face when designing them. So I mean. Despite the fact that it's like, they perform a seemingly mundane task, right? They just load code in memory and execute it. There are some challenges to contend with. The first of which is that, during the delivery phase, so while you're actually trying to get this payload onto the target machine, usually that's going to be done via spear phishing. And if that's the direction you're going, this payload is going to be exposed to signature-based detections, in the form of mail filters, and stuff that's scanning through the email that you're sending out. It also may be exposed to automated behavioral analysis. So automated sandboxes, essentially what they do is they take your payload and they actually execute it in a controlled environment. The reason why they do this is that whereas if you're just looking for signatures, you're going to get these like brittle signatures, but that are kind of easy to evade. But in this instance, if you're looking at what the program is doing while it's executing, you're actually looking at behavior, which is a little more difficult to hide. And finally, during the delivery phase, your payload is going to be downloaded and saved to disk, and you have to do this without triggering AV or getting caught by EDR or whatever. So that's the final challenge. And then once you've done that, you have to execute your payload. So the payload is going to be executed from disk. Usually, if it's like a phishing payload or something like that. Although typically in-memory operations are a little better. When you're just one of the challenges of your initial access payload is that you can't really start that way. So you have to start from disk a lot of the time. And you have to do this without triggering antivirus or endpoint detection and response, aka EDR. In Windows environments, you're also going to, application whitelisting is pretty much ubiquitous if you're operating within like an Active Directory environment or dealing with Windows. What this means is that you're going to have to find a way to bypass that, and that usually means relying on something called the concept known as live off the land binaries and scripts, or LOLBAS. Essentially what these are, they're just like utilities, they're binaries that come packaged with the operating system. And they're usually just designed to fulfill some benign role, but you can actually, what makes them special is that they have some functionality that you can essentially leverage to do something that is useful for you as an adversary. So in this case, there are several live off the land binaries and scripts that can be used to execute payloads in various interesting ways. So that's fortunate that you can rely on that. You can use that to bypass application whitelisting. The problem is that most of these pretty much restrict you to programming languages and execution methods that get filtered through the Windows Common Language Runtime, or CLR. And CLR, if you're going through the CLR, you have to contend with Microsoft's anti-malware scan interface, or AMSI, which just kind of like examines all this stuff that's going through. So that's yet another obstacle that you have to do. So in a lot of ways, getting this initial payload working and running, it can be very challenging, despite the fact that you're trying to do something that's seemingly simple. It's almost paradoxical in that way. And finally, I mean, you should assume that your initial access payload is going to be discovered. That's just a safe assumption to make. So your payload really should be able to withstand manual analysis in the form of threat hunters, reverse engineers, and the like. So with that in mind, all these are none of these are obstacles that are insurmountable. I mean, there are ways to contend with all of this. It is a bit of a cat and mouse game, but you know, it's something that you can get around. The problem is that successful evasion techniques do not last very long. They have a tendency to get stale. They have a relatively short shelf life, and this is because if you're doing your job right, defenders will eventually, learn from what you are doing as a red teamer and write detections against whatever TTPs you're using. So, those like really cool new TTPs that you drop. If you're doing your job right, this will actually improve their security, and they won't work forever. If you're using the same TTPs for years and years, well, you could argue that you're not really improving the security. But yeah, that's a whole other thing. But so defenders will eventually catch up to you, and what this means is that your payloads are finite. They have a shelf life, and that's good. And specific payloads, right? So we were talking about TTPs there, right? But specific payloads that you write have an even shorter shelf life, because at some point, someone's going to write a signature-based detection for that particular, assembly that you dropped on an op or something like that, and that's relatively easy to do. I mean, from relatively, right? I mean, from an adversary's perspective, what this means is that reusing payloads is likely to get you burned. So, this is where what this means is that initial access payloads are typically, kind of a pain point for offensive teams, and that's because, you have all these challenges that you have to overcome, and the ways that you overcome these obstacles, the methods that you use essentially are not going to last, and you typically have to write them by hand, or at least modify them by hand on an engagement per engagement basis. And code reuse can be problematic, and there's a lot of moving parts. There's a lot of I mean, despite the relatively simple purpose, if you've ever looked at like the source code for doing like process hollowing in C#, you'll see there's a lot of code involved, and there's a lot of things that can go wrong. So there's code reuse is a problem. You have to do a lot of stuff by hand, and there's a lot of moving parts, despite the fact that you're trying to do something relatively simple, which is kind of paradoxical. So to kind of contend with this problem, I was actually just kind of like researching payloads independently, but at some point, I just had the idea to work on this new tool called Drop Engine. And essentially, the goal of Drop Engine is to address this problem by providing a malleable framework for creating shellcode runners. So if you ever used like Cobalt-Strike, for example, one of the things that makes like Cobalt-Strike great is the fact that just about every aspect of your agent that you're placing on, that you're using on the target machines that you're operating on, can be modified. You can modify traffic profiles. You can modify essentially how it's dealing with like using name pipes and whatnot. I mean, like just about every aspect of its use, you can customize it in some way, and by doing that, really get a lot of use out of this one tool. So I guess the core idea was to try to do something similar with initial access payloads, and the core idea is to identify discrete payload components. So basically, like examine like your typical payload and say, what are all the parts that you see in this payload that kind of repeat themselves across every payload that you ever write, and identify those and turn them into modules. And as a bonus, provide built-in obfuscation, encryption, and symbolic substitution capabilities, which makes it easier to evade signature-based detections. And in the case of encryption, makes it easier to evade human analysts. And by doing that, we greatly extend the shelf life of those individual payload components that we're writing. So how would something like this work? To kind of think about this, right, we have to talk about how payloads are built. This is actually, the interesting about this project, this is less of a red team project than it is like a software development project, because like we're actually not really trying to do a whole lot of crazy stuff here with the actual the payload itself. We're just looking at kind of the abstract design pattern here. If we think about the anatomy of a payload, at their core, initial access payloads are relatively simple. They involve two major steps, which we talked about. You load the shellcode into memory, you execute it. A little bit of terminology that I'm going to throw out here. From this point onward in this presentation, we're going to refer to the routine that performs these two actions as the executor function, just to kind of make things simple. So there are many ways of achieving shellcode execution. You've got DLL injection, you can spawn a local thread, you can use process hollowing, thread execution, hijacking, all kinds of stuff. But we actually want to abstract away specific details like this. We don't really want to focus on them quite yet, or because what we're looking at is actually for more of a bigger picture. Also something else we need to consider, we mentioned that we need to contend with application whitelisting, and that really means that we're limited to formats that can be executed by LOLBOS, low-level land binders and scripts. So what this means is that our initial access payload is really going to require three basic components, and you can kind of see my diagram here on the left here. We're going to have the shellcode runner. Technically, the whole entire thing is a shellcode runner, but just for the sake of labeling things, we'll refer to this outer wrapper as a shellcode runner. That's going to be LOLBOS specific, right? If it's an MS-build payload, that's going to be like an XML file, basically. If it's an install util payload, that's going to be a C# file that's compiled into an assembly. But you have your outer shellcode runner, and then you have your payload main. That's your application entry point that's going to call your executor function, and really everything else that gets called within your payload, but we're not going to worry about everything else yet. It's just these three components. And then finally, you have your executor function, and this is going to load your shellcode into memory, execute it, and give you essentially, that's the meat of this payload so far. So Drop Engine implements these basic components as base classes. Essentially, what I've done is I've taken these three components and made it so you can inherit from them and derive modules from them. And what this means is that you could just write a module, and you can use any executor type you want, wrap it in any shellcode runner you want, and the overall structure of the payload remains the same, despite that you have a lot of different options as to how to actually implement all of this stuff. To kind of give you an example of when I'm talking about the structure, this is I ripped this direct. Well, there's supposed to be a link to his GitHub, but I guess like it's getting cropped on the bottom because it's PowerPoint and Zoom. But yeah, this is from 0x13 Steve Flores' GitHub. It's from a project called MoveKit. This is just an MS Build runner, right? And you have your outer wrapper, which is what we talked about here, right? And this is just your XML file. You have your payload main, which is just importing stuff and calling this executor here, and then you have your actual executor function there, your shellcode inject. So, and this can be interesting. I have to switch back and forth here a little bit. I'm actually going to stop sharing for a second and then reshare from Hyper. Cool. So, yeah, I mean, you're going to see a lot of other stuff here, but if you look at the overall structure of how things are done, we have our payload main components, have our runners. We can break them into individual discrete components like that, and we'll kind of go into more depth into this in a little bit. And then of course we have our executor functions, which I don't have a whole lot of them in there quite yet, but that's okay. So I'm gonna stop this and then attempt to share this again. Okay, there we go. And then hit from current slide. Okay. So we've identified our discrete components here, right? These items here. We also want to throw in encryption capabilities. So it's typically a good idea to leverage encryption when creating initial access payloads for multiple reasons. Basically, you have your shellcode that is going to be executed by your shellcode runner, and if it's something you don't necessarily want to, a lot of these are going to be like binary payloads or something like that. And you don't necessarily want to have to throw that whole entire thing out just because that particular signature is detected by antivirus. So what we do is, one way of hiding that from signature-based checks is by encrypting it. But the other advantage of encrypting your shellcode is that it makes it more difficult for human analysts to reverse engineer our payload. Remember, we need to assume that the payload is eventually going to get caught. And when it does, we want to make it as difficult for the reverse engineer to pick this apart as humanly possible. What this means is that our updated payload execution process is actually going to involve a few more steps. We're going to load the encrypted payload into memory. We're going to decrypt that payload using the encryption key to obtain plain text shellcode. And then finally, we're going to load that plain text shellcode into memory and execute it. So the extra step here that we've added is this encryption function. So if we're going to use encryption, this introduces yet another thing that we have to account for, and that's key storage, derivation, and retrieval. When we leverage encryption to protect our shellcode, essentially this is going to require us to provide our payload with one of the following. It's either going to need to be able to derive the encryption key somehow without actually storing it, right? So it's not going to store it, but we need to be able to obtain the encryption key somehow. It needs to be, if we can't do that, it could possibly just retrieve the encryption key from some other location. So we could provide it with that capability. Or we could just store the encryption key itself in the payload. Now, obviously, this last option is not ideal because, if you're storing the encryption key in the shellcode, if someone in the payload, then someone compromises the payload, then they can decrypt the shellcode, and you're just adding an extra step, but you're not really, making it terribly difficult to pick apart. So let's talk about this first option of it, right? We mentioned the use of the first option is to derive the encryption key. One really great way of doing this is the use of environmental keying. This is like so environmental keying has been around for a pretty long time. There's a lot. If you just look up like malware, environmental keying and just Google it, there's just tons of papers written about the subject. I think the three most relevant projects to check out, though, in terms of like prior work that's like really relevant to red teaming, would definitely be, well, Ebola is the classic one. So if you look up Ebola GitHub, like that one is going to come up really, and environmental keying, that one will come up. The other one is Spotter. That one was released fairly recently, I think like in 2018 or something like that. And it pretty much does something pretty similar. And then also there's I think like Leo Lupik has some a blog post where he talks about this and also expands off of those. But so the idea with environmental keying is that you actually derive the encryption key either entirely or in part from values in the environment. So what do we mean by this? Well, let's say that by attributes in the environment, we're talking about usernames. So for example, you could use the currently logged in user that your payload is running as part of the encryption key. You could try to obtain the external IP address from where your shellcode, your payload is executing, and use that as part of the encryption key. You could make sure that you're actually on the right computer by deriving the encryption key in part by using your internal FQDN. I actually even you could even use the moon phase or something like that. You can but essentially what this lets you do, it does two things. One, it makes your payload very, very resistant to analysis because your encryption key is now no longer being stored in the payload, and essentially they'd have to essentially like if you're setting encryption key to the value of the hard drive serial number, that means that you'll be able to decrypt and execute your payload on a specific machine that has that particular hard drive plugged in. But if you're an analyst and you just have a copy of this payload, unless you know what specific machine you're going after and what the serial number is, you're essentially forced to attempt to crack that encryption by guessing the value of that serial number. So it makes your payload super hard to crack, and the added advantage is that it's very targeted. your shellcode is only going to be decrypted on machines that match the key's specific attributes, or if someone sits there brute forcing for a very, very long time. So I'm now going to set the first live demo of this over Zoom, no less. This is going to be interesting. All right, so I'm going to do a couple things. First, I'm going to show you my setup that I'm using for this, because I think that's important, just so that you all know kind of what's going on here. So I'm going to stop sharing for 1 second, and I'm literally going to share. Well, can I do that? Okay, actually, yeah. So the first thing I have to show you, security settings on this machine that I'm using, because that's actually very relevant. And you should see it. Okay, let me try sharing this again. Oh, you know what I can do? Yeah, here it is. Okay, I got it. So as you can see, I don't have cloud delivered protection because I don't want the stuff I'm working on at the moment to get shipped off to antivirus analysis land, essentially. So that's turned off, as well as automatic sample submission. But this is a brand new Windows 10 install. Have real-time protection turned on. Tamper protection is turned on, so you can't disable it. But I do have an exclusion set up, and I want to explain this really fast in case you're wondering why certain things are working. So I have one exclusion here, and this is this directory demo AV include. So essentially what I'm going to be doing during these demos is I have 4, and I'm going to have to now switch windows that I'm sharing again. So you should see Hyper right now. There's 4 terminals. I'm going to try to make this a little cleaner. So in the top left, this is just for my benefit. That's essentially, I'm trying not to anger the demo gods. So I am keeping as much of this stuff in a text file. I'm going to run the commands that are in there rather than trying to just guess. This will be relevant later. This is going to be a remote key server, and you can kind of, we'll talk about that in a second. This is a Metasploit instance. So this is, so we're actually going to use Meterpreter for this. So like every AV engine under the sun should be able to detect what we're doing, essentially, is what I'm trying to say. We're just using the payload we're going to be using is going to be just a plain Meterpreter reverse HTTPS. We have to use HTTPS because the actual unencrypted traffic will be picked up immediately. But so that exclusion that we're seeing, Hyper's being difficult. I might have to, is going to be in this directory here. Demo AV exclude. And this is because we're going to be building this payload, and although the payload was generated here, the second I SCP that payload over onto my main machine, which is what you're seeing in this top right terminal here, Defender would just nuke that. And I really don't want to just keep turning Defender on and off every time I have to do a demo, which is because that's just I'm trying to make this go as smoothly as possible. So the kind of compromise here is that we're going to be pulling our actual shellcode out of demo AV exclude. But when we execute it, that's not where we're going to be executing from. We're going to be executing outside of that exclusion folder. Okay, with that out of the way, let's show you how to go over. Let's go over how we'd make an environment like a payload using environmental keying. So essentially, the first thing we're going to do is get a list of available modules, right? And just run this, and these are all the different payload components we can choose from. So let's say that we want to use environmental keying. We want to essentially grab let's do the FQDN because I have that written down, and my current username. So we're going to derive the key from that. In that case, we could just do this. We could do Python drop engine. I'm going to break onto a new line here. Specify that our shellcode should be, in that demo AV exclude to shell. We're going to use an interface. So the interface, I'm specifying this command interface. That's like literally the glue that holds everything together. You know, if you're working in C#, you're going to use the C# interface. Don't worry about that too much. But we're going to say C# runner interface, right? And then we're going to also look at just like this encryption key. So we talked about. So we need an encryption key and a decryption key. So the EQ keys we're going to use are going to be this external FQDN that we talked about. And notice I'm using more than one. And we'll kind of go into how that works in a second, right? We're also going to use the decryption keys, which is essentially these things, but written in C# because, you know, we're just going to copy these, put them in there. We're then going to need to select a cryptor to encrypt our shellcode. So we're going to say cryptor AES. We're just going to use AES-256. That should really be named AES-256, not just AES. I should change that. And we're going to use a decryptor. So decryptor C# original AES, which is the corresponding decryption function that we need. Finally, for our shellcode runner, we'll go ahead and use MS-build because that will save you from having to compile something, which will take extra time. And then we're going to need a mutator. We haven't really talked about mutators yet, but we will. But for now, I'm going to say mutator string. And essentially what that's going to do is going to take all the variable names in our finished output and change them to a random string. So it just makes it a little harder to signature on. And that really is, oh, we also need to specify the actual username and external FQDN that we're trying to use for our key. So I'll put my username as well as FQDN, and I'm just going to copy it from here. And hopefully this didn't update in the last time, like in the past hour or so, but I don't think it would have. And finally, oops, all right, I forgot something. We need an executor function. Yeah, so we need that executor function that actually executes our shellcode. And we're just going to use C# virtual alloc thread. So just going to essentially make a call to virtual alloc, virtual protect, and all that, and spawn this new thread. And we're going to make our output file example.csproj. And that's going to be our MS-build file. Cool, looks like it ran, didn't get any errors. If you look at our example csproj, here is an obfuscated MS-build file. Actually, I should probably kind of show you what this is actually doing. I'm going to do mutator null, which basically means don't mutate anything. But yeah, so you know, basically here are all the different components that are stacked together. Here are your decryption keys and your decryptor, and your executor, and everything else, right? And then here's your actual payload itself and payload main. Essentially, all this is just being rendered into the payload by Drop Engine automatically. And finally, run everything down there. I want this to be random because I don't know demo gods, I guess. So make that a random one. So now we're going to set up our handler. Use exploit multi-handler, payload, first CTP, lhost, set L port 443, which should be correct. And then we're going to say exploit-j to start our handler in the background. And then we're going to actually run this using MS-build. And there we go. Now, just to kind of, in case you don't believe me, like that this is actually doing something, I'm going to kill everything here. You know, that was a bad sign. Well, whatever. If I copy how do I enter nano? All right. You know what? I'm actually deviating from the demo right now, and I think that's a bad idea. We'll get back to this if we have time. No, actually, you know what? I'm stubborn. Let's do the. Yeah, if I copy demo AV, exclude empty shell, and let's just copy it up one level. We should get an alert. Or perhaps not. Maybe we might have to run it to get the alert. But yeah, I'm not going to sit here tinkering with this. Let's get back to PowerPoint. Okay. from current slide. So that's our payload with basically like custom built payload with environmental keying that we literally just created in like a second. So mutator modules, right? We mentioned also that we're using should there be, I guess not. Okay. Ignore me. I could have sworn there was something else that I was supposed to talk about there. Okay. Yeah. So like the other thing, essentially what we've just done. I mean, we've said, here's the executor function we want to use. Here's the shellcode runner we want to use. Here's the encryption decryption routines we want to use. And by the way, we want to derive our keys from these two specific functions, and we're going to pull this stuff together and make it into a payload. And by the way, randomize all the variables in variable names in that payload, and just run a command, and then it just does it, and then voila, you have a payload. The way that we did the actual the changing of the variable names was using basically modular symbolic mutation. So Drop Engine supports the use of mutator modules. That, I mean, essentially what they do is that they every module that corresponds to something that has like variable names or function names has a mutator method that gets called in the back end by whatever mutator module that you select, and the mutator module then systematically goes through and takes like a list of variable names and maps them using some algorithm. The algorithm is irrelevant, just it's module specific, and then when the actual and returns back to that module, the original module, that mapping, like a dictionary of like, here's all your variable names and here's the stuff that we've mapped them to. And then what happens is that when that module gets rendered or into a rendered template, and that's how we're building everything. It's using Jinja templates. We are essentially what's going on is that it looks at that mapping in order to figure out what to name the variable. So this is pretty cool because it allows us to create payloads that are circumvent signature-based detections pretty easily. I only have like 3 supported methods in there right now: row 13, the random string, and also symbol substitution using a word list. Null mutator doesn't really count because it just doesn't do anything. It's a null mutator. It's primarily there for debugging purposes. And kind of already demonstrated that, but if you want to just go over, just once again, like what that looks like, take this one that we just did, just print to the screen instead of an output file. So for example, here's your, actually, let me use, I've got another piece of shellcode that isn't so long that we can use for demos. Yeah, so, here's your random strings. If you wanted to use row 13, these look awful lot like the variable names. To use a word list, you actually have to specify a word list when you do this. Let's use US cities, and that will, now all of your variable names are correspond to US cities. A better use of this would just be to find make a word list that actually are believable variable names, but I don't know, this is better for doing a demo. Let me go back to PowerPoint, and let's move on from here. And let me just make sure. Okay, cool. So let's talk about some more keying techniques that we support. We talked about environmental keying. Remote keying, it's also very neat. Essentially, instead of deriving the key from some place in your environment, you're actually going to retrieve the encryption key from some remote location, either over HTTP or HTTPS, DNS, or some other communication protocol. This is actually, if you have well-designed non-attributable attack infrastructure, it actually makes this method pretty effective. You could place the key server behind a redirector and only accept requests for that key on very specific, for a very specific profile of traffic that's being sent to the redirector. If you want to make it even better, you can use a one-time remote key, which is a variant in which your key server, which is the server that's hosting these remote keys. And by the way, you want to have one key per payload, and Drop Engine does support that. So keys should be unique to the payload that you generate. But essentially, the one-time remote key variant, once that key is successfully retrieved from the key server, it actually is deleted from the key server. So the key server goes back into its database and just nukes the key. And what this means is that any future requests for that key are either going to be ignored by the key server or return some kind of junk data, or you could even at that point respond to that kind of request by returning a redirect. So you could do what a redirect would do and redirect that request to something innocuous, like like remotely hosted jQuery or something. Like, look, it's just jQuery, right? But so I mean, there are obviously some obvious advantages to doing keying this way. It's very resistant to analysis. The encryption key is not stored on the payload file, and it's hopefully being protected in transit using TLS. It's also less targeted, right? While highly targeted payloads are good in a lot of cases, sometimes they're not. Sometimes you don't just want to attack the computer of that one person that has that particular hard drive or username. Sometimes you want a little more breadth. And in this case, you don't have to limit your scope. I mean, you should limit your scope regardless, but I guess what I'm saying is like the scope isn't, implicitly limited by your keying mechanism at this point. I'll show you how this works in drop-ins really fast. And I'm going to go back to my screen here, go back to Hyper. And so in the bottom left, we have this what looks like a Flask app. It's a really, really basic. I honestly didn't put a whole lot of time into this because I was just trying to get the proof of concept out the door. But this is our remote one-time key server. And what we're going to do here, execute a very similar payload to what we just did, right? Hang on, let me. Yeah. So we're going to grab this. And this is, as you can see here, well, it just ran. But what we just did, we created a shellcode using our M2 shell, like our interpreter shell that's in that M2 shell.bin file. We use pretty much the same attributes we used last time. The difference here is we actually added some keying components. We added a new key here, which you can see right here. It's the eKey one-time remote HTTP and the corresponding decryption key, which is your DKey remote C# OTK HTTP. And essentially what this is doing is it's just providing functions that will attempt to reach out to this server right here that is running in the bottom left to retrieve this encryption key. And it's going to use that by using a specific identifier that's unique to your implant. So that, essentially what this guy down here is going to do is look in the database to see if that identifier exists. And if it does, it's going to respond with the decryption key and send it back to our payload. And then, it'll be deleted from the database. So if subsequent requests just won't be honored. So let's run that really fast. We just kind of prep the bottom left here, make sure we don't have any stragglers either in our sessions or. Oh, okay, cool. So we're going to run our handler, and I'm going to rebuild this really fast just to make sure everything looks up to snuff. It does. And we're going to call it MS build once again. And there we go. And you'll notice here this traffic showed up in the Flask app, and that is our server going back. That's our payload retrieving the key, right? Now let's go ahead and kill this session right here. Right. And the reason why I'm doing that is I want to show you what happens when we've already retrieved that remote key. So what we're going to do now is we're going to just kind of demonstrate if we happen to curl for that same value, right? Let's say we do a curl request to 127. This is running on localhost, so we can just do this. HTTP // We're not using SSL at the moment. And oh, you know what? We'd actually need the implant ID, wouldn't we? Oh no, here it is. Yeah, let's grab this implant ID right from here. Cool. So we have everything we need to make this work. And you'll see that we don't actually get a response this time because it's been cleared. All right. So back to our PowerPoint. We've got about 20 minutes left. Open this up for chat phone about 10. Let's go back here. Current slide. So one thing you'll notice is that we're actually using multiple encryption keys here, or it seems like it, right? Because we're specifying these different key types and combining them to create a final encryption key. We're doing this using something that I like to call key stacking, which is the practice. And this is just key stacking is just like a label. I'm sure this has been done before, like a million times, because it's really not that complicated. Like it's pretty simple in practice, and we'll see that in a minute. But essentially, key stacking is the practice of combining the results of multiple keying methods to create a single combined keys. So for example, let's say we have one key that's comprised of 4 parts: the hard drive serial number, external IP address, a not stored in the payload file, so it's a stored component, and also a one-time key that is retrieved over HTTPS. Well, in that point, we essentially would just make 4 method calls within our payload to 4 different key derivation functions, concatenate the results together, and by doing that, we'd have one encryption key that was derived from all these different sources. So one advantage of doing this is it gives us a little more security. It's difficult to compromise. Disadvantage is kind of complicated. If you're doing this by hand, like it's just adding more moving parts to the equation. But once again, since we're using a framework, it makes it a little less complicated. And essentially, what makes this possible is that the actual architecture that we saw at the very beginning, it has been updated a little bit. So remember, originally we just had that shellcode runner and a payload main in there and a executor function. In this case, we still have our shellcode runner. It's our outermost wrapper. That's our Lulzbot specific script that encapsulates everything. But we also have our payload main, and within that, we now have, you see here, we all have all these DKey functions. So we have a DKey1, DKey2, all the way through DKeyN. It's an arbitrary number of DKey functions. And essentially the way that this works is that, each key part is extracted from each of these key derivation functions and passed to the decryptor function along with the encrypted shellcode. That combined or stacked key is then used to get the plain text shellcode and it's passed to the executor. So, really it's not too bad, and we already went over key stacking. So let's talk about pre-modules and post-modules. And I included the Cookie Monster here because, who doesn't like the Cookie Monster? Like really. So what are pre-modules and post-modules? Essentially, this is a concept. I mean, there's often when you're executing that initial access payload, right, that shellcode within your shellcode runner, there are things that you want to do first before you actually start trying to execute your shellcode. For one thing, you might want to perform sandbox checks. Like if you're trying to see if you're in one of those automated sandboxes, you might not want to. You might want to check for some known attributes of those sandboxes, such as certain file paths or number of CPUs or what have you, to actually see if you're in like a quote unquote real environment or in a sandbox. Also, we mentioned that this is likely going to be going through the CLR, so you might want to try to bypass AMSI, and that's something that you might want to try to do before you execute your shellcode. So a pre-module is hard to do. I mean, essentially, they are just subroutines that are prepended to everything else in your payload. So what Drop Engine lets you do is you can specify any number of pre-modules that you want, and these will just get run before everything else does. So for example, if you want to run a sandbox check and an AMSI bypass, you pass those both to Drop Engine as pre-modules. They then get executed, and then once they finish executing, and they are executed in the order that you specify them, by the way, which is pretty cool because you can actually control which order they execute in. But once they finish executing, then we execute the rest of your shellcode here. So Post modules, they're pretty much the opposite thing. Instead of being pre-appended to the beginning of the payload, we append them to the end of the payload. So that's useful for if there's something that you want to do after your shellcode terminates. So cleanup routines, log file deletion, modification, and both pre-modules and post modules should be completely modular and mutable, just like the rest of the payload's components. So you can mangle all the string names and variable names and however you want. And so if we're going to demo process of adding pre-modules, here's how you do it. Make this a super fast one. So for example, here, you can see if we want to create a payload that, let's say we want to run an AMZ sandbox check for, say like, check to see if we're in a sandbox by checking the minimum number of USBs that have ever been installed. If you, let's say we look for also file paths that can alert us to being a fan that we're in a sandbox. So we do a file path-based sandbox check. And then finally, we want to execute a AMZ bypass or the AMZ scan buffer bypass. We can just, append these here as pre-modules. And oops. That's okay. Should be M2 shell, not shell. Do it just like this. And essentially, actually, if you're curious what this looks like, I'm not actually going to save this. I'm just going to sprint it to the screen. So I can't, yeah, that's what I want to do. And then I'm going to use that really, really small shellcode that I showed you earlier. That's easier to read. It should not be from the exclusion folder because the small shellcode is not in the exclusion folder. And you'll see here that, here are your sandbox checks and your AMZ bypass, and that's all getting executed up here essentially. So that all gets done right before you run everything else. So once again, let's run our underspell payload. We're going to start up a handler, and we created it in the last step, so I'm not going to recreate it. And you see that it runs, so everything just kind of goes swimmingly because we're down to the sandbox. We go ahead and fill this. And back to PowerPoint, just wrap this up. We kind of did both demos at once, and that's all right. The last thing we're going to talk about is essentially how do you create drop engine modules. So the goal of the project isn't really to provide pre-baked methods for bypassing AP and EDR. It's really more, we did provide some example modules, but really, they're not really doing anything new or novel. And this is by design because the goal of this framework is to enable red teams to essentially maximize the value that they get from their individual payloads by converting them into reusable modules. And if you're a defender, this is useful too, because you can use this tool to quickly create large sets of sample payloads from which to build a learning strategy. So there are two types of modules that you can build, input modules and output modules. Essentially, input modules are anything that's going in before it hits your payload. So your encryption function is an input module, and whereas, for example, your executor function is going to be an output module. This is super important. Shout out to Marcelo Bipleader because his basically like the loader that it's using to build these is heavily based off of some of the stuff he's done. But the thing about input modules, they always have to correspond to one or more matching output modules, but they're really relatively simple to implement. As you can see here, what we're doing is we're just inheriting from we're building an encryption key module, and we're just inheriting from this base class, and then creating a constructor, which is just kind of setting the various attributes associated with this. All the argument handling is done on the back end. So if you want to pass command line arguments to your module, you just add an add arguments function. If you've ever used argparse in Python before, it's you could just add all these here. The parser is already initialized by one of the parent classes of your module. So you could just make calls to self.parser add argument and add all the arguments you want. And that will get parsed automatically, essentially, once your payload is generated. And then you have your generate routine. And this is essentially, well, for encryption keys, it's generate, but depending on the module type you're using, you're going to have your function that actually does stuff. Output modules, very similar, but even simpler. So the way the output modules work, this is the actual, these actually get rendered into your payload. They may potentially correspond to an input module, they may not, as in the case of like an executor, for example. But it's really just a simple 2-component design. You have a Jinja template and a Python file that stores metadata that is passed to the Jinja template. You know, so for example, here I've got a list of all my variables and imports and whatnot. And you know, that gets passed to the interface and then passed back and then loaded into the template in however format you need it. And then here you just have the path to the Jinja template that you're using. As far as actually like creating these things go, how much time do we actually have? I won't spend too much time on this. I mean, just a bit, if you want to create one of these modules, aside from the stuff, I guess what we haven't really shown you is the template, but you know, example, here's just an example module. It doesn't really do anything. But you know, see, all that you have to do is just set these attributes, and then you give it a list of interfaces it's compatible with, and then any input modules it's compatible with. Give it a list of all the variables in your C# file or whatever kind of file you're using. Really, it's not limited to C#. And then also give it the name of a template and give it a function and class name. In this particular instance, you have to do that. It's not very long. Then you have to create a template. Right, and so literally this is the process of creating a template, and I'm actually working on automating this, but that requires essentially you need to write something that can parse C#, and you know that's coming along, but it's not quite done yet. But for now, what you do, if you want to actually turn just a normal C# file into a template that can be understood by Drop Engine, you just find all your variables in here, just wrap them in this Jinja parameter. So you just say v, and then you kind of use the syntax here. So we've got variable Nick, we just kind of edit it like that, and then we can do the same thing here with variable N. Should be our only 2 variables there, and then we just do that once again over here. So this is kind of be painful for longer ones, but you know, the good news is you only have to do it once in that case. And I'm working on some ways to kind of automate a lot of that. Share screen, back to PowerPoint. And that's pretty much it. I'm going to, actually, this is a Zoom thing, so I don't really know. That's the location of the project on GitHub if you want to check it out. I think it's supposed to be like a Q&A thing right now, and I need to figure out how that works. So I'm gonna. Yeah,
basically, and once again, thank you so much for your time and for the presentation here. Excellent presentation. So for the Q&A, you can jump into Discord. It's going to be offline. Of course, there's a little bit of delay between the stream and when they can answer. And there's a lot of people actually already talking about the presentation. So
super cool.
Kudos. And for those of you also that probably just joined, please take a look at all the talks and all the activities that we have in our website. The description should be in the bottom of the screen, right? So in the description of the screen, all the links and related material. And also please join the conversation, as we said, in Discord. So we're going to go in a little break, and the next presentation will start in just a few minutes. Thank you again, Gabriel.